This is Forrest Mims' Engineer's Notebook, published in 1980, and this specific copyright here is very important to me for several reasons. I'm gonna just come right out and say it. Meet my new tattoo. It's easily one of the nerdiest tattoos I've ever seen, save for maybe Tom Crawford's from Number Files, Navier-Stokes. Tom Crawford's Navier-Stokes equation rib tattoo that probably hurt like hell. My family's generally very anti-tattoo, so I know that they'll hate it, but I love it. And I think it really cements my status here on YouTube as this maniacal nerd tech electronics guy who won't shy away from like high voltage projects. We should probably take some time to talk about what the heck that even is. So the schematic that I actually tattooed on myself is very simple. It's this one right here. All it does is output a square wave, and it's controlled by this variable resistor right here, and it's based around this 555 timer, which we'll talk about. It's very ubiquitous. I'll spend some time just discussing how all of this works in great detail, so stay tuned for that. But you're probably already asking yourself something. You're probably saying, oh, but you're Thomas Computes, you have all the servers and you put computers on plywood and call it a Kubernetes cluster. Why would you put something so simple on your skin permanently? Why not put a rocket ship or, you know, space? Maybe even like a function block diagram for a motherboard, or maybe even just a really stupid meme like that one, for example. Maybe someday. Stay tuned. Well, the answer is this circuit actually has a lot of personal significance for me. It's the first circuit that I can remember breadboarding out on my own as a kid, and it just led into all this curiosity with engineering. My dad and I would play with electronics when I was little. It's a really key part of my childhood, and I really have to thank him just because I think that inspired curiosity in engineering, and it's the kind of curiosity that I carry to this day, and I will keep having this sort of curiosity in engineering forever, and that's the whole point. A tattoo's forever, so is my curiosity, so is my drive in engineering. So thanks, Dad. I know you don't like the tattoo though. So I'm thinking, for old time's sake, let's revisit the circuit. Let's build it again. Let's do this, have some fun with it, and just see if make sure that the schematic that I got is actually accurate. I've got everything I need here. Here's what an actual 555 chip looks like. You see. Oh, it's really, really hard to read. Let me get this in focus. Oh, you can kind of see it almost. Anyway, take my word for it. This is a 555 timer integrated circuit. So let's just put that where it needs to go. And I'll build the rest of the circuit now. All right, here we are. And I am going to be using a Dell Dazeem to power this, so let's give it a shot. And I'll bet you, this is the issue. Yep. Always remember, LEDs are only work in one orientation, only one polarity. So you'll notice I have the variable resistor here. Oh, there you go. Yeah, so that's connecting them here. It really doesn't show up very well on camera. Let me fix that. Oh, this is so hard to do in front of a camera. And there you go. Yeah, well, the range isn't very good. I don't actually have a 1 mega ohm potentiometer, which is this component right here. This is a 10 kilo ohm potentiometer, so the maximum resistance that I can actually give it is 10 kilo ohms. So it doesn't have a whole lot of range. And you notice when I connect it, it's basically turns it off completely. But I increased the value of this resistor here, which controls, well, actually, you know what? Let's break into the schematic diagram a little bit, because this is just a bunch of components on a very, very old breadboard. Here's that schematic again. Notice the main components. There's one variable resistor, or potentiometer, however you like to say it, one standard 1 kilo ohm resistor, and 1.01 microfarad capacitor. Throughout the presentation, I'm going to kind of just represent the capacitor as a water tank because that's basically its job in the circuit, and it's a lot easier to kind of see what's going on. So for example, I'll have, here's a capacitor that's charged, here's a capacitor that's discharged. But when the circuit's turned on, it's going to be oscillating between this and this very, very fast, and we'll kind of talk about how it does that. So the charge and discharge cycles take time, and those timings are affected by both the values of the resistors, so R1 and R2, as well as the capacitance of the capacitor. So R1 and R2 control the discharge and charging times, and a big capacitor is obviously going to take a lot longer to charge and discharge than a small one. So when charging, current is going to flow from VCC through R1 and R2, and it's going to charge the capacitor that way, so through that path. And then when it discharges, it goes from the capacitor back through R2 again and down through pin 7, which at this point in the cycle, it's tied to ground. And we'll kind of talk about how it does that and how the 555 timer chip even knows how to do that. So here's a block diagram of the chip, and this is going to help me trace it out a little bit more easily and kind of show you what's going on internally. So the chip is going to contain a voltage divider that's made up of 3 5 kilo ohm resistors in series, and this is going to help achieve 2/3 and 1/3 reference voltage, which we'll talk about in the next slide. There's 2 comparators, and these basically compare voltage levels between the 2 inputs. There's one NPN transistor. Notice that it's attached to pin 7, so it's attached to the discharge pin of the 555 timer. And then because it's a transistor, we can kind of already see that this can be turned on and off to discharge the capacitor and also prevent it from discharging when we need it to fill. There's also a flip-flop with output and not output. So the output is that little green circle down there. And Q bar, so in electronics and a lot of things mathematics, if you put a bar over a variable, it means not that variable. So it's going to be the inverse of whatever the output is. So output and not output, or Q bar. And then there's an output driver, because the flip-flop is not actually producing a whole lot of current, so we need to boost that output signal to make sure that the 555 timer can actually do some things. So let's start with that voltage divider. The voltage divider is going to divide the source voltage into 2/3 and 1/3 reference voltage. So here it is, voltage divider. At that point, it's going to be 1/3 of VCC, or supply voltage, and at that point, it's 2/3. So if I were to, actually use volts, like actually an actual measurement of voltage, if I supply 12 volts to this 555 timer, that first point is going to be at 8 volts, and that's going to connect to the minus pin of comparator 2. And the second point is going to be at 1/3 VCC, which is going to go to the comparator 1. So we already saw that. So the comparator 2, the minus pin is connected to 2/3 supply voltage, and the lower is going to be at 1/3 supply voltage. Now what a comparator does is it checks, it compares the voltages between these 2 pins. And in this configuration, if the voltage at the plus pin is higher than the voltage at the minus pin, the output will go high, and the opposite will happen for a voltage that's lower than the plus. So if the voltage at the plus terminal is lower than the voltage at the minus terminal, then the comparator will not go high. It will remain low. So here's an example of how this works in practice. So I'm going to go through basically the 555 timer, that's oscillator cycle. At the very beginning, and remember, the capacitor is connected to pins 2 and 6. So this is the trigger and threshold pins. You'll probably come to see why they're called that in just a minute, but just keep that in mind. So we'll start with the capacitor being low. So the capacitor right here is at or below 1/3 of the reference voltage in this case. Because of that, the output of comparator 1 is high, and the output of comparator 2 is low. And that will mean that the flip-flop is basically being set. So when it's set, the flip-flop output goes high, and remember, Q bar is the inverse of that, so Q bar is going to stay low. And because the output of Q bar, so the Q bar is connected to the gate of the NPN transistor, this will also kind of act as an open switch and current will be unable to flow through it. Also keep in mind that pin 4 here is constantly referenced to VCC. With this flip-flop, when the voltage at pin 4 goes below VCC, or if it goes low, then that'll actually reset the flip-flop, and we don't want that. So for the purposes of this demonstration, this circuit, we're basically going to ignore pin 4 because it's always connected to VCC. Now I want to look at that flip-flop briefly and talk about what that does. So here's an animated dissection of that component, which is basically two NOR gates where the output of either gate is connected to one of the inputs of the other gate. And there are two inputs and two outputs of this circuit, whose actually the scientific name here, this is an SR latch, and SR stands for set and reset. So when we set the circuit, Q will go high and stay high until we bring reset high, which will reset the bottom NOR gate and bring Q low. And doing this, as you can see, also brings Q bar high. So whatever Q is, Q bar will be the opposite. Going back to the circuit, we've already started part 1 of the process. At this stage in the cycle, the capacitor is beginning to fill and things are starting to happen. At this stage, comparator 1, which is referenced to 1/3 of VCC, turns off as the minus input goes higher than the plus input. Now there's no current going to the set pin of the flip-flop or SR latch, yet its state doesn't change just yet. Now the capacitor is at or above 2/3 VCC, which will trigger comparator 2's output to go high. And that will reset the flip-flop. So Q bar will actually now go high, and that will drive the output high, so it'll drive pin 3 high, and that will also engage the gate of the NPN discharge transistor, which will allow current to flow through pin 7 to ground. Remember, the capacitor's positive terminal is also connected to pin 7 through a resistor, which will limit how quickly it's able to discharge. So when that NPN transistor is enabled, current flows from the capacitor through the resistor, through the transistor, and into ground. So that will also make the voltage in the capacitor start to fall as it discharges. And as the voltage in the capacitor drops, the output of comparator 2 will go low as the capacitor begins to drop below 2/3 of the source voltage. Comparator 1 is still low because the voltage in the capacitor is not yet below 1/3 of the source voltage, but remember, the SR latch will hold its output until it's once again set, which is just around the corner. Finally, here we are once again at the beginning of the cycle where the whole process starts over again. Comparator 1 will go high, triggering the flip-flop and bringing the output of Q bar low once again. The transistor is closed, so, well, actually open, so it doesn't let current through, and the capacitor then is able to charge once again. It's pretty neat. And it's that simple. I mean, maybe not entirely simple, but what's for certain is that the circuit's really easy to build, it's cheap, it's reliable, and it's ubiquitous. You see this thing everywhere. I mean, you see it in like simple blinker circuits like this, of course, but I've also, like, I'm sure old cars probably used a 555 base timer for turn signals. You know, speed radars actually use 555 timers. I've made stun guns with this circuit before, just a 555 timer, like giving the pulse that drives a larger MOSFET. It's everywhere. The 555 timer has a lot of meaning to me personally, and I'm sure to many other electrical engineers. I mean, we all started learning with this and have just, you know, expanded our careers beyond based on this tiny little circuit. So go get it tattooed on your body, why not? To me, this chip is synonymous with creativity and wonder, and I really do credit it for being the foundation of the science, technical, creative person that I am today. You know, you might pray to God, but I pray to the 555 timer. I'm sorry, this was supposed to be all cute and sappy and wholesome. You know, just imagine just little Thomas there in his closet in his bedroom, just playing around with these, destroying capacitors, blowing them up, you know, maybe setting some fires accidentally. Who knows? And then just understand that that boy grew up and got a tattoo of the very thing that got him interested in science and engineering. It's mwah. Anyways, that's it for me. Keep an eye out for the zany, wacky things that I end up doing in 2023. I'm sure you'll love all of it. So, bye-bye. So let's revisit this circuit. Let's breadboard it out. Let's have some fun with it and just, recount the past 20 years of my life and shit.